Today, I would like to share some tips of how to get most out of Qdrant, because there are a lot of questions, and we just wanted to make sure that you are using it in the best way possible. So I will be sharing some of my experience, but also answering some of the questions that you have already asked on our Discord, just to make sure that it's not a blocker for you, and you can focus on the business value instead of checking out the docs. So hope to have some interesting session. Please feel free to ask some additional questions on top of that. Would be very happy to answer them as well.
Thank you. Yeah, I just wanted to remind that I'm monitoring the chat on Twitch, so I will be more than happy to ask all the questions you have to Casper directly. So feel free to use chat, and happy tutorial.
Great, thanks a lot. Yeah, so basically, I would like to go through all the steps that you may see in any sort of semantic search pipeline. So there are a lot of processes that have to be implemented somehow, and definitely the first step that you typically take is the upload of the data. And for the purposes of today's session, I prepared some notebooks, so that will be as practical as possible. And I would like to share some code snippets that you should have already implemented, I believe. And maybe I will also show how to configure Qdrant, how to set up some collections to achieve the best performance possible. And for the purposes of that session, I've just prepared an H&M data set. This is actually taken from one of the Kaggle's competition, and it contains data with images that have been vectorized using some neural models and some additional metadata in Qdrant's terminology called payloads. And this metadata payloads typically contain things like the category that a specific product belongs to, and all the other stuff. And vectors come from the images. And that's basically it when it comes to the data set. I'm not really going to dive deep into the details, but from your perspective, this is just some vectorized information and some additional attributes that might be quite useful to filter by them with. And starting with the data upload, this is the first process that has to be implemented in any sort of semantic search application. And if you have already checked Qdrant, you have probably implemented such a process at least once. So it all starts with creating a Qdrant client instance. The instance points to some sort of running Qdrant cluster, or that might be also a local Docker container. Doesn't really matter, since the functionality will be completely the same no matter if you use cloud or self-hosted version of it. And if you use Qdrant client, the official Python package, then you just need to create an instance of Qdrant client and point it to a specific URL. In my case, this is going to be a local host, since I decided to launch everything using a Docker container. The next step is the creation of the collection. So basically, all the data that we store in Qdrant is stored in collections. If you are familiar with SQL, I believe everybody does, then that might be thought as some sort of SQL table. So each collection should contain the data describing some similar objects with similar meaning. And in Qdrant, every single object has to be described by at least one neural embedding, one vector representation. So that's why we also need to provide that information while the collection is being created. So first of all, we provide a collection name. This is just hard-coded to be like test collection. So then the name is just put into a separate package. But that doesn't really matter, because the name of the collection is not really that important. But the important part is the vectors configuration, in which we need to provide the size of the embeddings and also the distance function that will be used internally to compare the similarity of those vectors. And this is important to be set beforehand because this distance function is being used in order to create a specific graph-like structure that is used in order to provide you with uh, effective and performant semantic search. Uh, we use HNSW, and HNSW stands for Hierarchical Navigable Small Words. And this is the data structure that allows us to store the vectors. So vectors which are close to each other will have an edge connecting them. And by that, it makes it easier to find some similar examples then. It's an approximation of k-nearest neighbors. So you cannot really, we cannot really guarantee that you will always receive the best results possible. But with a proper setup and the default values of Qdrant are chosen, so it works in most of the cases. It works properly in most of the cases. You can expect that you will receive the best results in like over 90% of the times. So basically, the simplest setup will look as following. We have a client instance created, and then we create a collection. The method is called recreate collection because if you call it twice, on the second call, the collection is going to be deleted and then created again. And it's quite helpful if you are still experimenting, just because you can reuse the same collection name over and over again. And the collection is created quite in really fast, just because there is no data put into it, because that's another process. And another part of that code is just iterating through all the objects within the collection. But here I decided just limit the maximum number of objects to 50,000. That's enough to show the performance gains while using different configuration. And there's also a separate function, batchify objects, that just iterates through all the objects and create some batches out of that. Basically, this is configured to use the batch size defined in a separate package. And this is, for the time being, it is set to 500, which is a reasonable amount, I would say. Then we are just iterating through those batches, and those batches are just sent into the same collection using the absurd method of the Qdrant client. And for that method, we need to provide the IDs, the vectors, and the payloads. This is not live coding session. As you may see, I just set this Jupyter notebook in order to calculate the time spent at some specific cells. And in this case, it was taking like 13 minutes to upload this 50,000 vectors with those payloads. And I have to say, those payloads are quite huge. There are various attributes available, and maybe in some of your applications that will be also the case. And we are also going to cover the topic of the payloads later on, but basically there are some mechanisms that allow to use those payloads in an efficient way. But basically, this is a simple process that we will see several times today, and that basically iterates through the objects, create the batches, and then send them into Qdrant instance just in order to save them into the database. And that's basically, this is like the simplest ETL process you could imagine. And overall, it takes 30 minutes to execute that cell. And when we now check the status of the collection, we can see that the collection status is green. That means that all the processes, all the optimization processes are done. And basically, we also have an information about the number of vectors. This is my mistake. I just made a function that iterates and limits the number of vectors, but I put the condition in the wrong place. So this is the number that I provided beforehand plus 1. But this is just the wrong use of the conditional loop. Sorry about that. But we also see that this has been split into 2 segments, because Qdrant and the HNSW graph is split into multiple segments. what allows us to perform the similarity search in parallel, because those segments might be reviewed by different processes at once, and the results might be then combined together. That also allows to make it scalable, because we can split those data into several shards, into several machines running in the same cluster, and then just combine the results to using this specific protocol, and that will make everything way faster, iterating through the objects. And I even increased the batch size by 2. I just decided that I don't want to put 500 objects at once, but I want like 1,000. The reason for that is that when I tried to use 1,000 with the default configuration and HTTP protocol, I was getting some timeouts. I wanted to avoid that, so I just reduced the default batch size to the number that makes sense. But here with gRPC protocol, we can increase that easily, and that will be still supported. And this is not a maximum. I just multiplied by 2, but it could be even multiplied by 4, and that should be still handled properly. And the rest is exactly the same. We are just abstracting the batches one by one, and the code that didn't change that much except for this specific line. And with this setup, we could reduce the time almost by a half. We are not spending like 30 minutes on upload, but less than 7 minutes. And gRPC protocol is actually the preferred way of interacting with Qdrant if you do not care that much about the debugging possibilities. Of course, if you use those REST models, it's way easier to debug that. But in any production load systems, gRPC protocol should be the preferred way of connecting, and that's just a single change in your code base. Now, when we check the collection status, we see that this is yellow. That means that some optimization processes are still running, but the rest hasn't really changed that much. But we can go into another optimization. That's something that we quite often just suggest to use to those people who are dealing with millions of embeddings. By default, Qdrant won't create any segment, any segment index if the size of the vectors which are not indexed is lower than a specific threshold. And by default, it's set to 10,000 kilobytes. Right now, with this additional configuration of the collection, I'm just setting it to 1 million kilobytes. So this is relatively huge number, and that means that no optimization will be done during the data upload, because Qdrant will just store all the vectors and perform the exact search without using the HNSW graph. But this is done just temporarily, because we want to absorb all the points and then eventually switch into a lower threshold for the indexing optimization, index creation. So then Qdrant will not put all the upcoming vectors while they are being uploaded, but instead process them once while all of them are already present in the index. So next time, so this is the next time when I'm using the same snippet of code. I'm still using this old client instance. That means that gRPC is still enabled. But so right now, the only difference is just this indexing threshold set to relatively high value. And right now, I was even able to get down to less than 5 minutes of the absorption time. But right now, you may see that the number of indexed vectors is 0. What means there are no HNSW graph segments that could be used while searching. So the search time should be relatively high, because we will need an exact match. So Qdrant will need to like perform a full scan on all your vectors, what might be quite slow. But the rest hasn't changed that much. Basically, there is one thing left that we need to do, because we need to update the collection in order to get back into this lower indexing threshold. I will set it up to like 10,000 kilobytes. And now the optimization process will run in the background, and that will index the vectors, and eventually we are going to have a collection with all the vectors being put into the HNSW graph. Here, as you may see, this is still 0 because this optimization process is just taking some time, and I was executing those cells one by one. So that might be misleading, but if you just switch to a different threshold, then at some point this will be already put into the index. And that's it when it comes to the data upload. The more important part might be the search operation, because that's something that you will do more often. And there are also some optimizations available if you want to do that. Basically, I will be preferring the gRPC protocol all the times, because that's just way faster. And if I just wanted to query the database, I would need to provide the collection name and the query vector. And that's actually it. It's basically the simplest operation that you can perform. And here I'm not really taking care that much about the search results, but I just wanted to calculate the time spent. And as you may see, a single query with that method and the random vector generated all the time takes in average less than 5 milliseconds. But by default, Qdrant returns the payload as well. And the payload might be a huge JSON object that is attached to the vector. And that means that we have quite a huge overhead on the data that is being transferred from the Qdrant server to the client. So we can also disable sending that payload over if we do not care that much about this metadata, and we just want to extract, let's say, the IDs of the objects that are the most similar to the query vector. And that reduces the time a lot, because by half. And if you do not want to have those payloads, that's a good point that's a good thing to do, just because it's just worthless sending the data through the network, especially if you pay for the traffic on some cloud providers. But there is also a different thing that we may do if we do not care that much about the search precision. The search process in Qdrant will be done in HNSW graph, and there is a parameter that we can set while searching. It is HNSW EF, and that may be set to a value, and that has a simple meaning. It's how many points should we check before returning the result. Here I just set it to a really small value. That means that Qdrant should review just 4 points, 4 neighbors before sending the results. This is really low value, and that means we won't be traversing through this graph-like structure that much, but we will just receive some of the results which are similar in some way, but the precision of that search won't be that important. But this reduces the time spent on the search operation quite a lot. And if we care more about the latency, we know that we want to perform the search as fast as possible. That's probably one of the easiest way to achieve that, but with the drawback of reduced search precision. And as you may see, this also reduced the latency. That might be quite useful. But I'm not trying to convince you to use such a low value for that, but trying to experiment with different values. If you really care about the search precision, you may also want to increase that. Here I set it to 1024, which is quite high. And now the average query time is even higher, a few times higher. It's 70 milliseconds. But I would expect that the results of that search will be almost identical as for the exact search. So this is quite important to know that that might be also controlled, and this is up to you to find the sweet spot between the search precision and the latency, but that can be done with Qdrant. Okay, and now if we wanted to combine the high search precision with a smaller latency, we could also disable getting the payloads of the objects. If we do not care about the metadata attributes, that's the first thing to do. And by disabling the payload transfer and increasing the value of EF to 1024, we could reduce the time by a half, almost by a half, and also keep a good performance. So there are various parameters that we could steer. And when it comes to the search results, this is how the typical response from Qdrant looks like. We basically limited the number of vectors to be returned to 3, and as a result, we received 3 instances of the scored point with the vector ID that we used, the payload, and this is the first time that we can actually see the payload, and this is a JSON object with some sort of attributes that are technically common for each product. And by default, there is no vector returned by Qdrant. Vectors are mostly useful for semantic search, so this is already covered by Qdrant. So we decided not to return them by default in the Python Qdrant client. But if you prefer having them for some further processing, that is also possible to be done. You can just provide a with vectors parameter, and that will be it. And here I just decided to have 3 results returned, and that's also the response of Qdrant. I have 3 results as a response, and that's it. But you might be also interested in using this payload data. And if you wanted to combine the vector search with some additional filtering on top of it, it's also possible to be done with Qdrant. You can provide another parameter that is called query filter. And here you can build your filter using must, should, and must not clauses. And must is an alternative for using AND operator. If I provided here a list of several conditions, they will be all they all will be required to be fulfilled in order to return a specific object. Here I decided to filter by index group name. As you may see, the index group name here is just a string attribute with a category that a specific item belongs to. And I just expect that only baby children items will be returned to me. So this is it. You can, of course, combine multiple conditions and build whatever works for you. There are several filtering mechanisms available, including geo-coordinates or range filters, but also full text filtering is supported. So as a result, I receive only the items coming from that specific group. But right now, you might be interested in seeing the difference between using the filters with and without the secondary indexes created. Right now, that's exactly the same query like I used before. I'm filtering by a specific field, and this field is of a string type. This is just a keyword. And this is the average latency I get. But Qdrant has also a concept of secondary indexes that you may create on the payload attributes. And this is fairly useful if you know that you will query on a specific field. Like in our case, if I'm going to query a lot based on this index group name field, I should probably create a payload index for it. And that's also fairly simple because I can use create payload index method with a collection name of the field that should be used by that index, and the type of the index that I'm creating. There are several types available. please just check out our documentation for some more details. But basically, you need to choose one just in order to let Qdrant know how to tackle that. We are schemaless, so you can actually attach any kind of JSON to your vectors, and that doesn't really matter. But because we are schemaless, you need to provide that information when you decide to create the payload indexes, just in order to enable proper search mechanism. Just a small insight here. Qdrant is quite unique because we integrated those additional secondary indexes, those additional filtering capabilities directly into the vector search phase. The other tools are using either pre or post filtering, but both have some drawbacks, and they were mitigated by integrating that filtering mechanism directly into a vector search phase. So this is a fairly unique mechanism for Qdrant, and that makes the filtering by payload attributes even faster. And right now, when I check the collection status, I can see that the payload schema is available, and there is a payload index created on a specific field, and it has a specific type, in our case, the keyword. And right now, if I use exactly the same query like I did before, but this time my field is going to be indexed, I'm going to reduce the latency of such a search operation quite a lot, because it is like a 25% of the original average latency that we tested out above. So this is a good idea to create those indexes, but you shouldn't be creating the indexes for all the payload attributes that you have, because the optimizer will always choose will try to choose the best index, the best payload index to perform your filtering. So you should be rather limiting some of your payloads that you know will be you will query by quite often. Okay, and right now this is how the results look like. Here let me come back to the previous example when we tested out the basic search with filtering. The highest score was like 0.35, around 0.35. Right now, with the filter applied on the indexed field, it's almost 0.4. That means that we are also able to increase the search precision by creating that payload index. If you are more interested in seeing some more about the indexing mechanism of Qdrant, you can also go directly into our website. But let me switch to another chapter, the memory optimization, because some of the vector databases will encourage you to keep all the data in your memory. That may work if you have thousands or millions of dollars to be spent on the infrastructure, but there are also some cases in which you do not care that much about the latency, and you can agree to have a higher latency, but keep the memory requirements a bit lower. So I'm also connecting to the Qdrant instance, but I'm also checking the stats of the Docker container that is running on my machine. And here you can see that the memory usage is around 650 megabytes. That means that this is the amount of memory that is required to support this collection that we created before. It has like 50K vectors with some JSON payloads attached to them. But we can also decide, while the collection is being created, we can also decide to store the payload on disk. So if we decide to do that, we can just provide on disk payload parameter and set it to true while we are creating the collection. Then put the data once again into the collection. And now when we by coincidence, I'm having some higher numbers here. That's a pity, but actually that allows you to reduce the time, not the time, but the memory requirements because the payloads won't be kept in memory, but will be stored on disk. Probably I was just testing out some different. I was just testing the output of that setup for a different collection. Yeah, it's just set on disk payload to true. So that was probably a mistake of me. Sorry about it. But basically, this is the strategy that you should be using. You can store the payloads on disk only, and that will limit the amount of memory that you will require. But there is also a different thing that you may consider. You can also decide to store your segments on disk, and we implemented that by using memmap. So the segments won't be stored on memory, but only mapped from disk, and will be just accessed, loaded from disk whenever that's required. And that's basically it. We only change the way that we create collection, and then we upload the data in exactly the same manner. So that really matters how we create the collection. You might be experimenting a bit from the very beginning, but then nothing else is changed. So basically, we just decided to map our index segments, and by that we were able to reduce the memory usage to a lower amount. And that's basically it. That's when it comes to some basic optimization for the memory usage. If you want to put some more vectors and you have some memory constraints, that's the proper way of how to do that. But search is not the only operation available in Qdrant. There are also two additional methods that you may find useful. I'm not sure if you are really familiar with them. So let me just share some info about the scroll method, which is simply used to access all the points that you have in a specific collection. As you may see, there is a difference because for search, I would need to provide a query vector. For scroll, I just provide a collection name and the number of vectors to be returned, and that actually iterates through all the objects that we have stored in that particular collection. And as a result, I receive a tuple, and there are the results of the scroll operation, but also the offset that I can provide to the same call later on. If I just decided to provide this offset, I will be iterating through the whole collection. So if you want to access all the vectors, that's the proper method to use. But for the semantic search applications, there is a different API, the recommendation API, that you may find useful because it allows you to perform the search not by using a single query vector, but instead you can provide the IDs of points, and there might be multiple positive and multiple negative examples chosen. But here you do not provide the vectors like a list of numbers, but some IDs of the points which are already in the collection. And by doing that, Qdrant tries to provide you the results which are similar to the positive examples and quite far away from the negative ones. So this is pretty useful for any sort of recommendation system if you have an information that this particular that you are looking for some items which are similar to those ones, but dissimilar to the other. And that's basically it when it comes. That's fairly simple. There is not huge difference between those endpoints, but they have a different semantic. So if you wanted to do that and try to use search mechanism for that, that might be also the proper way to go. And the last thing is the support for the batch methods. If you have several queries to be launched on the same collection at once, you don't necessarily need to call the search method several times. You can use the search batch and provide multiple requests. Here, I just decided to query for a specific vector, actually as a random vector, and another random vector. In the first case, I wanted to have the data returned with their payloads and just the top one result. In the second case, I wanted to query by a different random vector, this time without payloads. and I wanted to have like 2 results returned. Assuming that those requests are using the same collection, it might be done within just a single call to the API. And as a result, I receive a list at the first position there is a list of results for the first request, and on the second one there is a list of results for the second request that I made. And there is also a recommend badge, and so you can use that with all the methods which are actually supported with Qdrant. And you don't really need to handle that on the client side. And that's basically it. If you have any questions regarding Qdrant, I will be happy to answer them either right away or just on the Discord. You can reach me anytime. I'm present on the Labs Discord channels, so feel free to ask any questions if you have them.
We do have questions, so I'm back into the stream, and I would love to ask you while you are here. So we have one of the questions. Is it possible to store and the passage vector and the content of the passage also? If so, does it decrease the searching time? I hope you got that. If not, I can repeat it once again.
No, I think I got the question. Basically, yeah, you can use the payload for that. Payload is just some sort of JSON-like object, so we can store all the context if you require to do that. And that won't have much impact on the search time. However, if you want to apply some additional filtering on that passage, let's say, you should probably consider creating those payload indexes. Probably in that case, full text index is something that you are looking for.
Okay. And one more, not that quick question. So what will be the advantage to use Qdrant Cloud instance or deploy Qdrant local client on AWS EC2? What is the advantages of using Qdrant Cloud, like price, processing time, memory allowance, etc.?
Well, basically, if you decide to use Qdrant Cloud, then you have already a Qdrant support in place, just because that's managed by ourselves. So you don't really need to care much about the stability. We are also providing you an UI which is simple to use, and you can start and create some new clusters and manage your instances using this UI, which is quite convenient. But functional-wise, there is no difference. There is no difference between the self-hosted or cloud solutions. We want to keep the same functionality in both. This is just a different way, and the only advantage I would say is that you don't really need to worry about the infrastructure by using Qdrant Cloud.
All right. Thank you so much. Oh, okay. We have one more. Like the guy just took the train. If I understand, first we need to insert data via payload, and then we index the vectors field, right?
Not really. Actually, I just wanted to show this difference in terms of the latency. But you can also create a payload index beforehand, and then when you insert some new points, they will be also those payload indexes will be also propagated for those new entries. That's basically the way it should be done. Probably your data is going to change over time, so you actually are typically trying to create like an initial collection of data, then you create all the payload indexes which are required to make it performant. But eventually you are going to keep adding some new data, and you will be deleting the old stuff. So that might be created at any point whenever you feel it might improve the performance. So that's also quite important to perform some experiments. If you do not measure things, you might be creating too many indexes, and that won't change the performance that much. And of course, that has some overhead in terms of memory that has to be kept somewhere. So I would encourage you to experiment a bit, but it doesn't really matter. When you create those indexes, they will be always used.
Okay, sorry for stupid question, because I have the architecture of Milvus in hat. It seems very interesting and more mature than Milvus thinks. I guess it just updated on the previous question.
Well, I should thank you then. Yeah, Milvus is a different vector database provider, probably the first tool available, and yeah, they have some disadvantages just because the tool is quite old, and they made some decisions. But yeah, we are more flexible. We're actually solving some issues that the Milvus users had previously.